At all.
It was entirely on you. You know, the guy knew Cube inside and out, and he was, really good at domain.
Right.
But that's not what we know.
That's funny. So are you, speaking of Spark, are people here because of Spark generally? Topical? I mean, you want to hear it? Yeah? So there's one guy. Okay.
So just look at him when you talk.
Right. So about the Sparkitecture. Everybody else is in here because we're giving away a car, right? Did you guys look under your seats for the...
Are you going to cover COBOL?
Yeah. Pick 99B99. There you go. It's been a long time since I saw COBOL.
I guess we can start now. First of all, let me apologize for the date on that presentation. I didn't work on the slide. The original speaker couldn't travel to this event. So I just got back from vacation last night, and I was asked to present today, so apologize for that. I'm Ranganathan. Good morning, everyone, and thanks for coming. And I'm Ranganathan. I'm the product manager for Big Data Solutions at Hewlett-Packard Enterprise. And along with me is Jack Gudenkauf. He's our Big Data Services Architect. And today, we'll be talking about, spending a few more minutes about our solutions from an infrastructure standpoint for running Spark and the next generation workloads. And Jack is going to be talking about use cases that use Vertica and integrate with Spark. And I'm going to close out the session. And we'll have a few minutes for question and answers. So I'm going to start out with a statistic which probably is not surprising to many of you who have Hadoop deployments. In my role for over the last 5 years prior to joining HPE, I ran the technology and operations team for a previous organization. And this is not surprising to me that almost half of all Hadoop deployments struggle with getting data of value, integrating different data sources with technologies, and managing it all as a shared platform. So one of the first barriers to Hadoop deployments is the ability to quickly identify data of value. So the problem is exacerbated by the increased velocity and the volume of data. So you are the data is not static, you are increasing the data from multiple sources. And so identifying the data of value becomes a challenge. A lot of times, companies spend a significant amount of time probably changing the workflows, looking at different technologies to get that value out of data. The second barrier is the integration complexity. So this ties in with the first barrier, which is about how do I identify data of value? So you can start with your MapReduce jobs, but then you quickly move beyond that, saying, okay, SQL is a familiar interface for me to query this data. So let me try different versions of SQL, whether it's Cloudera or Hortonworks or MapR, or somebody like HPE, which offers Vertica, SQL on Hadoop. So there are different flavors of it. So you would start experimenting with that. And depending on your use case, you could have NoSQL data stores. You could have real-time streaming using Kafka. So you have an explosion of technologies that you have to deal with and integrate it with your existing systems. So if you happen to run SAP in your data center, now SAP HANA provides an in-memory platform. So now if you want to integrate that with data that's in Hadoop and you want to be able to query against both these data stores, then you have to figure out what's the best way to do that. The third barrier is about the complexity in the systems, because each one of these services scales linearly, right? So whether you're talking about Flume or you're talking about Kafka, which allow you to ingest data, you can have your own cluster of Kafka and Flume, in addition to what you have for Hadoop. So in addition to that, you have multiple clusters. So not many organizations stick with one cluster. You have multiple clusters. Most of these clusters have some common data, but not all. So you're duplicating data into multiple sources or into multiple systems. And now having to run your analytics workloads and quickly generate value out of this multiple silos becomes a big challenge. So what do we do about it? So the first step to simplify is to see if you can consolidate data, and that, with the data lake concept that allows you to do that is to consolidate all the data first, whether it's from structured sources, from your operational data stores, or from unstructured sources. Now, the vision of the data lake is to make the analytics possible on the centralized pool of data. But unfortunately, for a couple of reasons, the reality is that data lakes have not realized that value. And the two reasons why this is so is because the first of it is you need a structure or a data model for your data lake, right? So you just cannot store all your data in the data lake, assuming that you can run analytics. Although Hadoop is schema on read, you need some structure. The second is you need data management and governance. You need to be able to track where the data comes from, the lineage, how do you classify it, what format you have to store the data in, whether it's Parquet or ORC. You need to be able to store it in the right format for your acceleration of the analytics use case. The second problem here is about complexity, is about the compute aspect, right? As you start with MapReduce jobs and MapReduce workloads, but then you quickly move on to SQL on Hadoop or Spark, right, for streaming analytics. And in those cases, then you're moving from a conventional model where you scale compute and storage lockstep. You are looking at models where you need more compute, more memory to run your new workloads. So these are the two barriers to having a shared enterprise platform. So now, how does HPE help here? So if you look at the conventional wisdom, and this is something that Chris covered in the keynote earlier today, is traditionally you use a 2-socket server with 12 to 14 disks, and you build your Hadoop cluster, and you linearly scale based on your data needs, right? And then you could optimize some aspect of it by storing more data or going to more denser form factors of in the same configuration where it's still symmetric. You're scaling compute and storage together. But the problem here is with new workloads like Spark, you are wasting a lot of resources. You're wasting a lot of storage. You're having to increase your compute or memory for the Spark workload. So your existing architectures become inefficient for that workload. So you have multiple workloads to consider. So if you talk about a typical big data journey, you start off with ETL, ELT offload. You start using Hadoop as a landing zone. Then you quickly move on to real-time, near real-time event processing using a NoSQL data store like HBase. You start using Flume. And then if you want in-memory analytics, you start using Spark or a technology like Vertica. And then as your data volumes grow, you're looking to have some sort of tiering using hot, warm, or cold classifications. Again, this all means that you have to do that in your architecture or infrastructure that you've deployed, which becomes very inefficient. And lastly, you might have special use cases where you're talking about deep learning, where you might want to use special GPUs to run the machine learning algorithms. So for example, I think Yahoo uses special GPUs in their cluster to run against the same data set, and using Yarn to manage the resources, the pool of resources. Similarly, if you look at archival, Facebook uses erasure coding, and eBay has the tiering, which along with Hortonworks was presented earlier, I believe, session last year. So all of this needs to operate on the same data. So coming to where HPE plays here. So if you were to take all these use cases, which not only means consolidation of data, but also consolidating your workloads, starting with batch, then you move on to low latency workloads like HBase or Cassandra, or look at archiving the data that's not used as frequently into a heavy storage tier, or special compute or accelerators using GPUs. So the platform, the HPE's analytics platform, allows you to choose the servers that are optimized for that specific workload and for the specific use case or the requirement, whether you're talking about NoSQL workloads where you need low latency using Flash and NVMe technologies, or GPUs for accelerating your deep learning analytics. So it gives you a platform using open source standard Hadoop distributions, using Yarn's capabilities, the capacity scheduler, and HPE's own contribution to labels to allow you to run all of these, and more importantly, to scale as you grow, right? So when you start off, you might want to run on a platform that allows you to store all the data, ingest all the data, and then layer on the compute capabilities based on your workloads. So the benefits of this platform allows you to, as I mentioned before, is to consolidate all the data and give you the flexibility with building blocks that you can add on as needed based on your use case. And most of this is achieved through density optimized servers. So density could be storage density, where you have, in a 2U form factor, you have more disks. Or it could be density, where in a 4U form factor, you have multiple nodes, multiple servers. Or in a 2U form factor, you have multiple servers. So in that sense, I'll take you through a few examples in the next few slides which illustrate that. But the point is, as you scale your Hadoop clusters from tens of nodes at the start to hundreds of nodes, very quickly you're talking about power, cooling, data center capacity, and how do you optimize your infrastructure on one platform that allows you to slow down the capacity consumption of the data center. So let's look at the building blocks of this platform. So as I mentioned, you can start off with the 4200 platform, which is a 2U form factor, has up to 28 disks that can be added to that server. And that gives you a great foundation building block to store your data as you ingest it into Hadoop. And as you start bringing in workloads like Spark, you use the Apollo 2000, which has 4 servers, 4 two-socket servers in a 2U form factor for the compute and memory processing needs. So in addition to that, as you want to archive, you can extend your 4200s with maybe larger capacity drives. And then for customers who've already standardized on a balanced DL380 configuration, you can integrate that with this platform. So that allows you the flexibility to scale whichever way you want to. But I think for those people who are probably familiar with the conventional model of Hadoop, where storage and compute go hand in hand, that you don't really want to separate it out because of data locality. I think one of the biggest questions that people have is, how would this architecture perform, right? Where we talk about separating compute with storage. So we've done some tests with benchmarks, with industry standard benchmarks. And what we have here is we can show almost double the read and write performance using this architecture as opposed to a traditional architecture. And one of the key things that we find, especially from studies of the Facebook and the other big implementations of Hadoop, is most of the data that's accessed is probably less than 100 gig when you run your MapReduce jobs, right? And so data locality is not much of a concern. and with faster Ethernet networks, like a 40 gig network or a 25 gig network, you are able to get that speed, and which allows you to separate compute and storage. So now you have a single storage layer. You push down all your data into that storage layer. You can tier it as you want, and then bring only the data you need for the workloads that you need to process, for example, Spark or any other mechanism that you use on top of that. So, just as a comparison, if you look at a typical Hadoop deployment with a single use case like a data mart, you can quickly see how you can reduce the rack capacity requirements using the workload and density optimized servers. So with the Apollo 2000 and the 4200, you can get equivalent performance for probably half the rack capacity that you need for a small cluster. And as you grow, and specifically for most workloads, you get significant double-digit performance benefits. And as you grow, you can see that you get to optimize the layer or the resource that you need most. For example, if you need compute capacity, you can get a lot more compute capacity using the 2000s. And if you need cold data, you get a lot more capacity using the 4200s. So we moved from a traditional balanced approach where you have 2 socket servers with a number of cores and number of threads with a set number of disks to scaling out compute and density optimized servers and scaling out storage with storage density optimized servers. And specific to the implementation that we have and the contributions that we made along with Hortonworks in the area of yarn labels and using the capacity scheduler, this allows you to target these workloads to specific groups of servers. So for example, if you were running deep learning, you would allocate a yarn label for that group of servers, and you would run your workload over there, as opposed to running it on the same servers where you're running your batch workloads, MapReduce workloads. So coming to the topic that this deck was the title originally was designed to address, was about what does it mean for Spark. And with Spark, it gives you a platform for federation for multiple use cases, right? Whether you run SQL, whether you run machine learning, you stream data, or for graph processing. And you could store your data in different formats, whether it's Parquet, ORC, or HDFS. And then you integrate it with other enterprise systems like HANA, or Vertica, or Oracle. So now, when you talk about these technologies, then with HPE's platform on the server side, you can integrate all these technologies on top of this and be able to guarantee the performance for that specific workload. Now, in the next slide, Jack is going to talk to you more about a specific use case on Spark and how this technology or this architecture allows you to run those workloads specifically on the HPE platform. Jack?
Thank you. So I can get kind of a little bit of a sense of the audience and where your interests lie. If I can get maybe some quick show of hands, people that have existing Hadoop deployments infrastructure. Okay, it is the Hadoop conference. That was an easy one. Using Hive, Impala, Cloudera, Hortonworks, kind of a mix of, yeah, okay. And then Spark is an interesting thing to you, or you're using it now, or you want to, okay, mostly from the MapReduce workload, et cetera. Okay, cool. So I really love what my coworker here was talking about, because for me, whenever we're building an infrastructure architecture, it's really about the use case and optimizing for the use case, but being flexible and having extensibility and having a separation of concerns. And so where you want to move compute, if you're doing more machine learning and Spark, et cetera, this kind of flexibility will kind of resonate with you. So I'm going to go through kind of a solution that kind of came to be after years and years and years of having a lot of pain in building solutions and supporting them. Everything that myself and my team have ever built, we've had to support. So what I'm going to show you is highly reliable, it scales, and because we don't like to get called in the middle of the night. I don't know about you. So this architecture, if you remember anything from this talk, aside from like how busy this slide's going to be and how I completely violated all PowerPoint presentation of like a few bullet items to talk about everything, this is a really dense slide, but I did this because it's going to be on a single page, an architecture that I think solves a lot of problems from streaming in the data, from ingestion to scaling, and basically the intention of all data ingestion is for consumption, right? I mean, data without use of that data really has no value. So it's really about analytics and how you consume the data. So we'll talk about this as we go through. So new acronym for you, PSTL. You've all heard of ETL, extract, transform, and load. Kind of falling out of favor, but clearly it's something that we all need to do, especially from getting the data, transforming it, and loading it. ELT, where you might extract the data, load the data, and then do the transformations kind of post-loading, say in more of the data warehouse. More and more and more of processing is getting more near real time, and it's really about streaming and about ingestion of data and streaming more real time for more shortening up that ingestion time for the streaming of data to the time that it's consumable from an analytics perspective. So I'm going to talk about kind of prescriptive guidance and this architecture, kind of for the full stack. You know, think Kafka, Spark, Hadoop, and Vertica column restore, which we'll talk about. So the main thing here that I really want to talk about is parallelization through the entire stack. And you'll see, typically, you know, you have a MySQL database, maybe it's sharded, you have some applications, some Java applications, whatever, PHP, et cetera. You know, web, mobile, it's in the cloud. You have some source of data, right? And traditionally, you extracted that data. And that doesn't scale all that well. And then in a lot of our customer cases, you have some data warehouse, you know, maybe it's a column restore. Is anybody here using Vertica at all? Just want to get it, yeah? Okay, well, okay, good. Maybe Redshift, okay. Mostly data warehouses in Hadoop, I'm guessing, probably here, and you're using like Hive or, you know, maybe Pig or something like that for, okay, cool. So a lot of our customers, you know, the end goal is to have the data warehouse. I'm going to kind of start with this. Don't worry, it's a Hadoop talk. I'll get there. So, but there's all this stuff in the middle, right? Like, how do I get the data from this point to consumable, you know, analytics consumption, right? Because that's the end goal. So having a centralized data hub for this, as opposed to extracting in a Kafka cluster, you know, think of it as a kind of a persistent queue, if you will, that scales very well. It has some great semantics to it. Of course, it scales, which is great. And it's a durable queue, right? So as opposed to pushing things like a RabbitMQ or MSMQ where you're pushing things onto the stack and then you just pop them off, it's a durable queue you can keep rereading and from wherever you last left off. All of these particular topics I could talk about for like days, but I have like 15 minutes. So when they give me the hook, you know, hopefully we can just talk afterwards if you want to talk about this a little bit more. So ideally getting this data to some centralized place is the way to go, right? So how do we do that? I kind of favor JSON as a message format. It's a little bit verbose when you know, your keys and your metadata description is as much as your data. So one of the things that I like is Avro format. It's a more compact format, but you can send it as JSON. Confluent, which has done a lot of contributions in kind of the founders of Kafka as well. They have some nice ways to ingest. So just think about coming from like a web application. You can push those messages, JSON messages, through a REST proxy, which is nice because that scales as well. and it can encode it as Avro onto Kafka. So you're literally storing more compressed data onto Kafka, and over the wire, more compressed data is better, but it's still a JSON schema. You can store that schema in a schema repository, so you can evolve the schema over time with all your messages and tie that back for data at rest later on. The Kafka connector allows things like reading MySQL, and as data changes, it just sends messages directly onto Kafka. That's a pretty handy feature when you want to get some data in kind of a near real time as data is being written to a store like MySQL or even Vertica. And then of course applications can just write to Kafka, with the APIs, Java, Scala. Scala is kind of my favorite language these days. All the cool kids are doing it. So now we're getting some data in a common format, and we don't have to worry about the extract. How do we get it into our data warehouse? Starting talking about Vertica at this point. Vertica has a Kafka connector, which you can instead of taking delimited file formats and then copying that in bulk, which it does a famously good job of, you can just stream that data in. You can have a scheduler that just sits there and looks at data as it's coming in, real-time streaming from your external sources directly into Vertica. Everything you're going to notice in here that's like a blue arrow, and where I have a couple of them, it's parallelized. So what do I mean by that? It's not just distributed or scaled out into a cluster, but as messages are being written onto Kafka, they're partitioned, okay? So think of a big, long stream of data that's chunked up and partitioned across nodes. And as the Kafka connector for Vertica is reading it, it's reading it by partition in parallel. Now that's extremely powerful if you think about it, because now you can take data as it's streaming, read it in parallel, but what if you need to do some transformations on that data? Because you're going to assume that the data coming into this with this connector is exactly how it's formatted, and we know if we all deal with data in this room, right? There's different formats. Nobody's ever going to send it to you in the right format. You need to do some transformations. I love Spark for transformations. It's a great model. Whether you program in Scala or Java or Python, or you like programming in SQL, I do for set-based logic, Spark is an amazing application. It's basically just a library extension. But Spark streaming, you can read those messages as well in Kafka, and typically micro batches, pretty near real time. But read it in parallel with the Spark application. The real power there, though, is that you're writing functional transformation. So just think of like a UDF, or you're, just transforming like an epoch or something to a timestamp. It could be simple transformations, obviously, or more complex transformations. But those functions are being applied to the data in parallel, in real time. So you're reading chunks of data and resilient distributed data sets in Spark, applying the transformation. So you're just writing functions, so you don't have to think about things like multi-threaded applications and how does this scale. Because at the end of the day, you want to be able to answer the question for your boss and say, can we just throw hardware at this problem and fix it? And if you can't answer yes to that question, your architecture isn't the right architecture and it's not scaling. I mean, I've been there a lot, that's how I know. When they say, I can give you a blank check, you want to say, yes, give me a blank check, right? But you don't want to say, I need to re-architect this system because we designed it in such a way that it's not scalable. Sorry, I tend to go right in the videos over there, so I don't mean to ignore everybody over here. So applying the transformations as it's streaming in parallel. So you notice parallel streaming transformation loader, just like an ELT, but it's streaming now, right? It's parallel ingestion onto Kafka, parallel reading off of Kafka. Now, what we can also do is do the transformations and put it back onto a new Kafka topic. So we transform the data in parallel, reshape it. This is where we get some value out of going from a data lake, semi-structured data, put it back onto a topic into Kafka, and guess what? Then with our Vertica Kafka connector, it just automatically streams into Vertica. Extremely powerful stuff. What else can we do with the Spark application? Well, because it's an application, we have code, we can iterate over it, over the partitions. We can read out of Vertica as well in parallel. So think of all the nodes in your Vertica cluster. Every one of these dotted lines is a cluster, so it scales out. That's the beauty of it, right? You can add more compute. You can tweak for storage. The solutions that we offer as well are reading in parallel from the Vertica nodes directly into partitions. So reading out in parallel, maybe transforming it, and then writing directly to Vertica, maybe not going back through Kafka. I think I'm probably getting low on time here. So that's a little hard to read. We like to build systems that are idempotent. and that have multiple solutions, whether it's colder storage or more for analytics for like an MPP columnar store like Vertica, or if you want to run Hive over your either colder data, or you have other bigger Hadoop jobs, or you want to do some machine learning in your Spark applications and store that. What we do is after we persist the data to Vertica, now Vertica doesn't have to be in this picture, just saying, we kind of like Vertica, we're from HPE. But as we write the data into Vertica, we've reshaped it, transformed it. It's now in format that looks just like a Vertica or any data warehouse table, or split it up. We also want to write it into Hadoop. Now, we tend to write the data directly, the raw data, as Avro data, because that's exactly what it looked like on Kafka, so we want to retain that data infinitely. So we write it in there. It also helps see if you have a bug in your ETL system. But then we also, because we have it in memory already in our Hadoop cluster, and we've transformed it that matches exactly what our Vertica tables look like, we store it in an ORC file format. It's a columnar format. It's much like Parquet. You can start as Parquet if you like as well. I like ORC a lot. There's a lot of things to like about it. It's a pretty compact format. You can store it as snappy compressed. It looks exactly like the data. One of the nice things about that is Vertica has a connector to read ORC files. So if you guys use like Impala or Tez or anything like that to read your data from Hadoop, imagine that you could do all of your Vertica analytics functions that are native to Vertica, but reading data from Hadoop ORC files. It's just like an external table. So that's pretty powerful, and it's pretty darn fast, as it turns out as well. So columnar store in the data warehouse, columnar store in Hadoop for your more semi-structured data, now structured data, and you can read between the two and do heterogeneous joins from Hadoop data to Vertica. Pretty powerful stuff. What if you have a data center boundary? You have another Vertica cluster, maybe it's another Hadoop cluster. It all works the same, right? Well, as it turns out, Turtle's all the way down. So you can take all your messages that are coming into Kafka, you can mirror them to your other data center, and then you can just do the dual ingestion or your Kafka connector to Vertica as well. Many solutions. The thing that I love about this architecture, it's really flexible, right? If you want to add compute to the Spark, you can add compute to the Spark. If you want to have send messages back onto Kafka and have them streaming, but the main thing is that everything that you see is read in parallel, it's transformed in parallel, so therefore it scales out, and it's written in parallel and read in parallel. Does that make sense? Sort of? Yeah, along the way? So if you think of like Lambda architectures where you're like streaming and then you have your batch and then you have to kind of reconcile them, this kind of really solves all of that, starting from streaming, doing your transformations, persisting the data, reading in parallel and writing in parallel. I think I'm probably running late on time or not, but just if it kind of makes sense and you want to talk afterwards, you had to do one of these, maybe not so much, yeah, sort of. So this scales very well. We're working with a lot of big customers, as it turns out, with this architecture. When I say working with, we kind of have this general framework. By the way, this is not that proprietary. I talked about this a year ago at the Big Data Conference. It's really kind of a generalized architecture. So there's nothing specific to HP, but we do provide solutions and services. So call me maybe, and we work with customers to like customize this. Maybe they want more storage in Hadoop, or they started with Hadoop and then they want to go to Vertica, or they don't want Vertica at all. So our team is all about providing solutions in a holistic manner for whatever the customer needs. So it may or may not have Vertica, but this is a general guidance and works extremely well with the existing knobs that you can turn with compute. So hopefully that sort of made some sense and resonated with everybody. But yeah.
Yeah, we can throw the session open for Q&A if you have any questions. Happy to address them. I think we have 5 minutes. I think they should be available at some point through the Hadoop Summit organizers. Yeah.
Any other questions? Yeah.
I have one question. It looks like from your hardware point of view, you put your different types of servers within one rack. I'm wondering what's the difference between putting them in one rack versus having homogeneous racks for different types and placing that way?
You could do that. So it really depends on how you want to design that architecture, right? So depending on what your data volume needs are and your processing needs are, you might want to plan out in advance on how you want to distribute them across multiple racks. It really depends on how fast you are growing. So there's no set rule to say. And there are ways you can tweak it, right? You could have homogeneous racks. And then because we use the fast interconnect, it becomes less of an issue. But of course, you have to consider availability. And if you have to consider situations where you have to deal with replication, there are things that you need to consider when you place the servers.
So you are connecting those servers using Ethernet rather than any proprietary cloud?
Yes, absolutely. Yeah, it's standard Ethernet. Yes.
Okay. And the second question is, when you do this kind of separation, how do you deal with local file system access from some of these software architectures like Hive or MapR and these things? They still need to write to local file systems.
It's completely abstracted because everything is HDFS. You mean the temporary data? Are you talking about temporary data? Yeah, so that would reside on the compute tier. So you would have.
Compute servers do have
Yes,
local
yes,
file
absolutely, yes. Yeah, we accelerate that using SSDs as needed because we find that gives you the best performance just for the temporary data.
Any other questions? Yeah.
Well, it's kind of, it's more like a blueprint architecture, or do you have some code associated with it, or it's just more like it's a blueprint of
So the question is this kind of just general guidance of an architecture, or do we have code around it? The answer to that is yes. So this is a general architecture that I find works extremely well. Our team in particular, we have a lot of the framework already built, so we can kind of bring that into a customer site and kind of extend it. It's an extensible architecture. That said, all of this you could build, out of the box yourself as well, right? With, Kafka streaming. You could use D streams if you wanted to with Spark. Spark, you can use D streams to read partition data from Kafka. We actually have a slightly different model of that. I think it's a little bit more efficient in our implementation. But primarily, what we do is first of all listen to what your needs are. And then help you build the best solution. But we do have like a bunch of stuff to like hit the ground running for you. Is the long answer? Does that sort of answer your question? Yeah. I talked about more of this in the BDC, and that is up on SlideShare. Somebody's asking about slides. If you want to see me wave my hands and talk about parallelism and RDDs and stuff as well, that kind of drills down on this.
So I have a question on the HP Elastic, the building blocks slide that you had. So if our existing cluster is all the DL380s, if we wanted to go that route, would we just stack the 4200?
Yeah, absolutely, and that's why I use that as one of the building blocks where you could repurpose that as storage nodes, right? So you could integrate that with the 4200s and the 2000, and you could add on top of that. There's nothing stopping you from doing that.
But is that like a seamless transition?
Yes, absolutely, because it's all based on Ethernet anyway, right? Yeah, it's all based on Ethernet. So the switching is Ethernet, so you shouldn't have a problem there.
So then the 380s become just the
Storage tier, yeah. Yeah, yeah.
2 minutes.
One last question.
Any other
Did you have a
questions?
question?
Yeah.
Did you have a question? All right.
Anything? What is the meaning of life?
Thank you for attending.